Next, we continue with the characteristic of the op-amp. So as the op-amp is the amplifier, so the one of the main properties is the gain. So as mentioned in the first video, op-amp has a very high gain. So very high gain. So it is designed to have a very high gain. So the gain of op-amp we can classify classify as two types. One is the open loop, and the second one is the closed loop. Okay, so what is the main difference of open loop and closed loop? So closed loop is the one with the feedback, and open loop is without any feedback. So open loop is there is no feedback from the output back to the input. So the if you consider the op-amp, this is your input. You have the non-inverting and inverting inputs, and then you have your output. So this configuration without any feedback, it is when you measure the voltage. Let's say you use the V out, and this is your V1, and then this is your V2. When you measure the V out, and then you calculate the gain is the open loop gain. So this is open loop gain. Okay. However, if you make a feedback, so if you make the feedback from the output to the input, so this is called a closed loop gain. Closed loop gain. So usually the feedback is done by negative feedback. So usually we do the negative feedback. So because negative feedback reduce the gain and improve many characteristics of op-amp. Okay. In the open loop gain, for open loop gain, the gain can be as high as 10,000. So 10,000 gain. But 10,000 gain in most of application is too much. Is too large. So why? Because let's say the input is a sine wave with the amplitude of let's say 1 millivolt. Okay, 1 millivolt. If you have the gain of 10,000, you have gain 10,000, so the output will become 10 volt. Okay, 10 volt. So is it a 10 volt? 10 volt is actually okay, but if the case of the input is, let's say we increase to 10 millivolt, so what happened to the output? Output will become 100 volt. So 100 volt is very large. So it's very large signal. Okay. So for a device, for electronic device, you have a DC supply. Okay, for example, in this op-amp, you have a DC supply plus VCC and negative VCC. So the the output of the device will be limited by the plus VCC and negative VCC. For example, the DC voltage here is 12 volt. Okay, this is minus 12 volt. So the output of this op-amp will be from the range of the minimum range is value is minus 12, and then the maximum will be 12. So if you have the gain 10,000, this type of operation is not suitable. Okay, you cannot get the proper output waveform. So there will be a clipping effect. Okay. So the op-amp, as the op-amp is an amplifier, so we can represent the op-amp using the general model of amplifier. So this is what we have discussed in our previous chapters. So for general model amplifier, usually we have the ZI, input impedance, and then we have the amplification effect is represented by the voltage source, voltage dependent voltage source. We have the AV OC voltage Vin. Okay, and then at the output we have the Z out. Okay, so same goes. This type of general amplifier can be applied to the op-amp. So here this is Ri is actually equal to Zi. A is the gain. R naught is Z naught. Okay, output impedance. Okay, so this is K. Okay, for the input impedance in the ideal op-amp, the value is infinity. So op-amp will have the infinity. Ideal op-amp has ideal infinite input impedance. Okay, for the ideal op-amp also has a infinite gain, and ideal op-amp has a zero Z out output impedance. Okay, so and then another item that you need to focus on is the input current. So input current, since we have a two input, so we have the input current at the non-inverting I plus here. This is non-inverting. This is I plus, and then we have the I minus is towards the into the inverting port. So this one, there's I plus and I minus. So because since the Zi is infinity for ideal, so this is equal to 0. So we have the 0 input current. Okay. So this characteristic is very important when you want to analyze the op-amp circuit. Okay. So next, this slide show the transfer curve of op-amp. Transfer curve. The word transfer curve, transfer means that showing the output versus input. So output will be your y-axis, and the input will be your x-axis. So this is a transfer curve. Yeah, transfer curve. Okay, the word transfer curve, transfer graph, or any type transfer function, usually it refer to the relationship between the output against the input. Okay, we have this equation. V out is equal to A, and the input is the differential between the non-inverting to the inverting. So we have this equation for op-amp. So this equation is a linear equation. So this is a linear equation. So you see here, this region is a linear region. So where this equation is applicable. But when the output voltage, if the output voltage is larger than the supply DC, so the output will be fixed at the supply DC. So this is what we call a positive saturation. Okay, so where the saturation start, where the output voltage is fixed in the positive saturation, in the ideal case, the saturation happen at plus VCC. Okay, same goes when the output signal is much lower than negative VCC. So there will be a saturation. The output will be fixed at the minimum voltage, which is in ideal case, the output will be fixed at the negative VCC. Okay, so this from the transfer characteristic, we can have two region. The first region is the linear region. So linear region where we have where the relationship between output and input is in the linear fashion. And then the second is the current is the voltage, output voltage will have only one or only two values, whether this is plus VCC or negative VCC. This is what we call a non-linear. So linear can be associated with the analog application, and non-linear is digital application. Okay. Okay, some of these characteristic has been mentioned, so we just emphasize it again. So ideal op-amp will have a infinite open loop gain. Okay, infinite open loop gain. Okay. And then ideal op-amp will have the infinite input impedance and zero output impedance. Okay. For the ideal op-amp, the saturation will happen at plus VCC. This is for positive saturation, or negative VCC. Is this a negative saturation? Okay. This output saturation voltage sometimes is denoted as V out saturation. So in ideal case, again, just want to make sure I get this right. So in ideal case, V out saturation is equal to plus VCC. Okay, minus V out saturation is equal to minus VCC. Okay, and then this high CMR is a common mode rejection ratio. For differential amplifier, the amplifier operate as a to amplify the difference between two input. Okay, at the same time, the circuit will have another mode. We call it a common mode. Common mode is the averaging of the two input, and then it amplify the average, the common mode. So ideally, we want to make the differential mode is more dominant than the common mode. So this ratio between the common mode to the differential mode is called CMRR. So this is high. Ideally, the CMRR is infinity, means that the amplifier operate only as a differential amplifier. Okay. Then the last one is high bandwidth. The high bandwidth is referring to the frequency, the operational frequency. So whether it can process a wide range of the input signal, low frequency signal, high frequency signal, or moderate frequency signal. Ideally, the bandwidth is infinity. Okay, so this table summarize the properties of ideal and compare with the typical, the non-ideal, or the typical value. So the gain infinity, but in a typical value it is about 10 power. This is 10 power of 6. So bandwidth is limited in typical properties of op-amp is limited to 1 megahertz. Output impedance is very high, but is around 100 mega ohm, and input impedance is around 100 mega ohm. Output impedance is around 100 ohms. And then the common this is CMRR. So CMRR is around 10,000. Okay, and then another is the noise. The noise is the noise in the input or in the output. So for the non-ideal, we have the noise of 1 microvolt. 1 microvolt. So why this noise is important? Because if your signal is very small, let's say is comparable with this 1 microvolt. So let's say your input signal is 1 microvolt sine wave. So this noise will overshadow with your overshadows your input. So at the end, your output will not have a clear shape as expected. Okay. So and then in this table is also showing some example related to the properties. For the gain, you can use as a microphone. So bandwidth is related to the ultrasound, and then so on. Okay, and the slide lists down several advantages of the op-amp. So one is no external element is needed for stability. So if you have the op-amp, so one chip of op-amp, you can just use it and get the good result, the good operation. So no need to design or combine with other element to stabilize the circuit. Okay, and then the second advantage is gain value varies with feedback to one of the input. Okay, so this is quite important advantage. So we know that the op-amp have a two type of gain. We have the open loop gain, and we also have the open loop, and we have the closed loop gain. Okay, open loop gain is a fixed value, but closed loop gain depend on the feedback resistance. So here the closed loop gain can be controlled. Or can be modified. Can be controlled or can be modified by changing the value of the feedback resistance. Okay. And then AC signal can be amplified without biasing. So actually this is the biasing is already there's already the port for plus VCC and minus VCC in the amplifier. So no need to design the biasing circuit. Okay, no need to design the biasing circuit for the device. Okay, and then output nearly zero when the input is zero. So this is actually for the op-amp. You need to do some optimization because there will be the DC offset, but in certain application this DC offset value can be ignored. Okay. So output can be in phase or 180 out of phase with the input. Okay, sometimes you want to have the in phase output and out of phase output. Okay, for the BJT, for example, BJT amplifier, for common emitter will have a negative gain. Negative gain. So this means that the output is out of phase, 180 degree. For other configuration, as a common base, we have a positive gain. So this is the in phase. So the output will be in phase of the input. Okay, when you use the BJT, you need to construct different configuration to get the negative gain or positive gain. But for the op-amp, you can be easily change this negative gain to positive gain by changing the connection of the resistor outside the op-amp. So it's much easier compared to the BJT circuit.